Good morning, everybody. First of all, let me remind you that this afternoon from 14 on, maybe 1 hour or two, according to how many people are here, we will be answering questions on the homeworks and the lab one. Remember that we have to present them on Sunday in the evening. Okay. Questions about this? So let me start now. In the last lecture we were talking about the PD classification, right? Basically we say, okay, we can put the systems into first order. So there will be some metrics here and some big vector field here which might contain several tensors, etc. And we have some system like this. In general, the dimension of the equations is bigger than the dimension of fields, unknowns. That's why, in general, we will encounter constraints. There are also equations where we have gauge freedoms, and in that case we have more variables. We might have more variables than equations, and some kernels in the system, but these we will not do. They can be treated also, but we will not do here. Maybe we'll say something at the end if there is time. But there are many systems that comes with constraints, for instance, electromagnetism. So it's good that we can treat them all in the same footing. So what we analyzed was these metrics here, because that tells us a lot about the system. And for this metric, we require that there is some covector NA in the space-time such that M, A prime, A, NA has no kernel. Okay? And then we try to find other vectors with kernels. And in general, one way of doing this is to take some combination like this, and try to find whether there is some kernel here. And you fix this K and move alpha, and do it for all Ks. And it could happen several things. There is never kernel, and these were the elliptic equations. There is one kernel, and these were the parabolic. And then there could be that there are many. And typically these are the hyperbolic. And though they came from studying second order equations, and they are classifying in a very particular set the equations which come only like parabolic, elliptic, and hyperbolic, the idea behind this is that along the kernels, right, some, let's say if you have a K, the whole thing, I'm just calling K this here. such that this has a kernel. That means, so there is a u such that this is 0, u this different from 0. Then there are waves propagating along this surface, right? K is a covector, so it determines some surface, right? This surface, say, are given by some function equal to constant, and then the K, you can choose it to be the gradient of S. So it's a covector. So there are waves that are going through this surface. Oops. There are waves traveling here, that is, the function u is constant along these things. So if it is like you are in the space, say at some point you are making a wave, and the wave is propagating this way here, so it's constant along these lines which are tangent to the surface. So this line, if this line is L, then we have LA, KA equal to 0. So this is a interpretation. So in elliptic equations we don't have waves. Parabolic is a special case we might discuss when we study parabolics. And then in the hyperbolic is a real waves. In the case of electromagnetism, for instance, it will be a plane wave. A plane wave given the K, a null vector, you have a plane wave going like this. Okay? So this is the idea. And in particular, we started to look at symmetric hyperbolic systems. And for that we say, okay, a symmetric hyperbolic system so this system is symmetric hyperbolic. Let's symmetric hyperbolic. If there is some reduction, the reduction is something which has an index down. So it brings from the space of equations back to the space of unknown, of variables. And a vector NA such that we have two conditions, RB A prime, M A prime A N is symmetric. So in these two indices for every A, right? And two, this combination contracted with an A is positive. And this we call a symmetric hyperbolic system. Let's see some examples of symmetric hyperbolic system, and then we go to the theory. So the simplest example you can think of is you are given a vector field, LA, in space, in any dimension. And you take some scalar function and you say that this is a function either of the space of or of the point or both. Doesn't matter. And so you want to solve this. And this is hyperbolic, symmetric hyperbolic, because the metric, there is just one equation, so there is a metric 1 by 1. And so the only thing I have to check is that there is a vector such that ln na is bigger than 0. Right? That will be the condition. So it's automatically symmetric, and then I have to check that there is a vector which satisfies that. And of course, I can always find a vector. What is the property, right? These covectors means that they are they form a surface. So the condition is that you have a surface. These conditions means that you have a surface. So let's say s equal to 0, and so you have a function, and the level set of that function for s equal to 0 is the surface, and the function grows to the upper part. So we have the gradient of s, and so what we need is that LA gradient A of s is bigger than 0, so L has to point to on the direction of s growing, right? So the condition is that whenever you are in a point here, the vector L is leaving the surface to the future. Okay, that's the condition. So once you have that, what do you do? Well, given a vector L, what you can do is to compute the integral curves of that vector, right? So the integral curve will be something like that. We'll come here, and we will, let's say, this curve. So now you have a curve here that you parameterize with some value lambda. So what you have is in coordinates here, you have that the coordinates is equal to the component of this vector, and so that equation says that d xi d lambda di of u is f of u, and you can put here xi of, well, let's put everything here. So this will be at the point xi of lambda, and the point itself xi of lambda. And so here this is just du to the lambda is equals to f of lambda, where lambda enters here and here, right? And this is an orderly differential equation. So we know how to solve this, given u at s equal to 0, okay? So the idea is you give u here in this S surface. Oops. You give u here, and then you can evolve along each line. So you take any point, you evolve, you compute first the integral curve using this along this, right? And then you compute the u, you evolve the u using this equation. Okay? So this way you get a solution. So this is in fact the Cauchy problem. So the Cauchy problem works very well here. And this is simplest case. And you can think, okay, which are the characteristics of this system? So the characteristics are the ends such that this thing is 0. So when does it happens? Well, you have the vector L at some point, and then you need the n to be some surface that contains the vector. And since it contains the vector, it will contain, so this vector is tangent here, so it will contain the integral curve. So if there is an integral curve here, the vector is in any place is tangent. It's tangent, and this is contained in this plane, so this line will be contained in this characteristic. Of course, the characteristic, if you move from point to point, can change, right? Can do anything. But you will have to keep the vector tangent to it. And that's why we say, okay, the evolution, you see from this thing here that this point is evolving along this line. So to know the value of u here, the only thing I need to know is the value of u here. So this is, we will see in more detail in a while, but you see the domains of influence of this point is all this line, and the domain of dependence of this point is the line also, called back. Right, the influence is this line to the future from here, and so this is the domain of influence. So if I change the value here, I can influence what happens here, nothing else. So it's this line, the red line from here to the future. And the domain of dependence of this other point is everything that the value here depends on, and the values here in this to the past, this line to the past, from this point. We will get more into the concept of domain of dependence and influence. It's clear? Questions? So the characteristics are planes which contain the vector field L. So the vector field L is tangent to these planes. And along these lines is where the propagation of information goes. The waves. So the next example is also the same kind, but repeated 3 times. And this F, let's for the moment think of F that depends only on the position, not on U. Or at most they depend, say, on U1 and the points, U2 and the points, and U3 and the points. So you can solve each one independently. So at every point I will have 3 vectors. L1, And the matrix, right, is a diagonal metric because I have three things here. So there is a metric for U1, a metric for U2, a metric for U3. They are diagonal. So this is already symmetric hyperbolic, symmetric, and to be hyperbolic, what I need is a surface. Let's put another color here. I need a surface here, such that what? The three vectors must be pointing in the same direction. If I have this, then I can do the evolution, because I put something here and I can have the three quantities here. I evolve this one in the same way as before, this one in the same way, this in the same way, and I get the three quantities. And of course, once you realize this, then you say, okay, I can put for the L2, say, a dependence on U3, because when I am evolving the three simultaneously, I will know for every point here simultaneously, I will know the value, say, because, say, which one would answer? If I need the value of U2 here, I can compute it from the point here, say, following this line. So to compute here, I will simultaneously not only evolve around this, but also evolve the L2 around here, and I will have a point. So this surface is a nice Cauchy surface. But notice that I could do something else. For instance, I could take, instead of this, take the L1 here, L2 here, and then I'll take minus L3 here. And that I can do because I can multiply this equation for anything. So I can multiply by -1, right? This is the same equation. So if I do that, my new L3 will be pointing down. And so now I can do the same, but I can choose a Cauchy surface which is like that. So that the three vectors are pointing, well, not very nice draw. Let me draw it better. I will draw the surface first, and then I will draw the vectors. So one vector is like this, the other vector is like that, going out, and the other vector is coming like this. So this is minus L3, L1, L2. So this, any surface actually do it if you change the sign, except the surfaces that touch one of these vectors. So I have to keep away from the vectors. Okay, so in this case, in this particular case, I can solve for it as long as I'm not touching the vector. So these vectors cannot be tangent to the surface. Okay, questions? So let me try now a more complicated example. This is an example where the vector L itself depends on U. For instance, if you consider a Barger's equation, which is dt of u plus u squared dx, u dx u without a square. This is Barger's equation that we will evolve this numerically. Then we can solve for these systems. I don't know whether I have it here. Yeah. So now what we say, okay, let's consider some data, some surface. Some u0. Well, this is a bit tautological, but let's consider some surface. Well, let me do it, and we'll do this after. So let's treat it in 2 dimensions. So we have the vector L and the function f, that is a function that depends on the points, and u. And this is the L of u, right? So here we can make a trick, which is very interesting. We can go to 3 dimensions. So we go to R3. We go to R3, and the u will be basically the set. So we define a function tau, which is just set minus the values of u. So this is given x set xy. We given a point here, we consider a solution, and this distance is tau. So if you take the gradient of tau, we get minus ux minus u, the derivative of u with respect to y, and 1. So now we have a problem in 3D, which is this one, and so this vector L twiddle and this problem, right? Here we can put f as 0, or we can put f, doesn't matter. So what we know is that along this vector in 3D, the tau is constant, right? This is for f equal to 0. It's constant along the integral curves of L twiddle. Right? So now we draw this L twiddle, and what we have is we can rule it. We can take L and get a surface which is ruled by L, right? So you take L, make the integral curves of L, and these are these lines here, and so you take a curve like this, and this will represent a solution, right? Because then we can get the u from here, from this plot. And in general, what we can do is to say, okay, take any line. Suppose the L is going like this. Take a line so that is this line. Let's call gamma this line. Let me use another color here. Let me call gamma this line. This line. And I choose it in such a way that it's nowhere tangent to L. Right, so L is always going out from here, never tangent. And so I take this value here of tau, or set xy, and then I look at the value of L here, and I integrate, right? And so I get this line. I take the value here, integrate, and so I get a surface. Given the values in this line, I get a surface. So this surface depends on gamma. And this is a solution, right? Because from that I can get a solution. Just taking this value and projecting down to the surface, say, okay, this is a U I need. Okay? So this way I get solutions. Suppose I take two gammas here, gamma 1 is this one, and gamma 2 is this one. If they intersect at some point, then I will have the L is the same here, so this integral curve is common to both. So if they intersect at some point, they intersect in a line, and this line is tangent to L. So this line, the L goes like this. So whenever this surface intersects, that will be two different solutions. The line in common is L. The problem with this way of constructing the solution, so every time you have something like that, you construct a solution, right? So you take a gamma, and that is given, for instance, in this case, I could give you in x0 equals to u0 of x, right? And that will give me this line. Remember that tau, the surface constant of constant, this is a surface of constant tau, is z minus u, right? So if I give u here, then I construct it, and this is constant, I know the height, the z. So I know this, and from here I can get a solution, right? In our case, for the Vargas equation that we were checking before, if I give u of x0, t equal to 0, like u0, this line is never going to be tangent, so it's okay, I can give this as an initial data, because this vector is different from 0. So this we build solutions. But there is a problem here, that suppose I can start with a nice surface here, do the evolution, and while I'm doing the evolution, saying, following this line here, this surface can become in the future of this other, can fold like this. So if I want to know the value here of the solution, I will find two values, or three values in this case, right? I will find, so imagine that z equal to 0 is here. At this point xy, I will find this solution, and this solution. So it's multiple value. So it's not a proper solution because we want a function. We have a problem. We have many solutions here. So in the real life, what happens is that you start with some nice solution like this, and the solution starts getting, for instance, like that, and here your normal calculation, if you are assuming things smooth, it will break down, because this will get infinite, the derivative will get infinite here. So you have to do something, you do some shocks capturing methods, And that what it does is selects one of these solutions. And so, for instance, it will select this one here, and then it will select this or this, probably this. And you will follow this. In the future will be like that. Sorry, I'm not drawing it. Will be, for instance, like this. So there will be a shock, a discontinuity moving in this direction, for instance. We will see this numerically. But here, when we do that, we are choosing one of the solutions, one of the possible solutions. And there are other problems we will see later here also, because here we can have many solutions too. But that I don't know how to represent it here. It should be possible to represent this. I don't know how to do that. So the takeaway thing from here is that when you have a nonlinear theory, you might have shocks. You might create discontinuities. And there is nothing wrong with that. You see from here that will happen. You have multiple value solutions. So you have to choose one, unless you want to live with several possibilities. Okay. Questions? So here I put the construction. This is in the notes. It's well discussed in the note at length. Not well, but at length. Here I discuss how to build local solutions. Local meaning smooth. Not without shocks, before the shocks. So imagine you have this, you want to build this rule surface. So this gamma here will be a function of t and s. I don't know why I'm using two. Gamma of s. So t and s. T and s. So think of many curves in t parameterized by s. So you want to solve this system. So what you do is get a first curve, gamma of 0, so t equal to 0 s, and you say, okay, my first curve will be this one, the gamma naught, and you want to solve this problem here up to some gamma st, which is this one, which is very close. So what you have, so let's do the construction here. What you have is the u that you have in your equation is set of s and t through x and y, okay? Because these are parameters. So when I move s along this, so it's some function here, and then I move t, which is along the lines. So and what I have, actually, when I'm solving this problem, this problem here upstairs, is some x of st and y of st, right? So I need to invert this relation, because what I want is s of xy and t of xy, and what I'm having is this relation. So I have to use the implicit function theorem, and invert this relation. And for that, what I need is the Jacobian to be invertible, to have an inverse, right? And the Jacobian of this transformation are the derivatives of x with respect to s, y with respect to s, x with respect to t. So to have it invertible, what I need is that this, the determinant of this metric is different from 0. You compute the determinant, it's very easy, it's this by this minus this by this. And now you use that the derivative of y with respect to t is the component Ly, right? And this is this in here, and you have minus Lx, the derivative of y with respect to s. And these things, what are these? These things, these are the tangent vectors along s. The tangent vectors along t are the L's, and so these are the tangent vectors along s. So this is, for instance, in this point, the tangent vector will be this vector. Let's say at this point, the tangent vector will be this. This is the vector dx to ds, dy to ds. So it's the description of this curve parameterized by s. So what we are saying, you call this vector s. No. P, whatever. What we are saying is that this equation says that L scalar P, sorry, no, not scalar. Says that Ly with Px minus Lx Py should be different from 0. And that means that Lm is not equal to alpha times P. So it will work as long as L is not tangent to the surface, the initial surface. If L is not tangent, then you can invert this matrix and compute a solution for a y, for an submeter. Okay? So that's the condition you need. That's what we discussed before. So geometrically, what you do is you need to put a curve, compute the u in this curve, and check that the L is not tangent. And then you can do this. And so you get this ruled surface, which is a solution. So locally, you can always find solutions. If u is okay, you compute a solution. But we know that then, in very simple cases, like the Barger equations, you will find this problem. So the most you can expect to have a smooth solution are local in time results. So that's what we are going to get in the end. And if the solution has this problem, then you have to continue using shock methods. But before, we have to learn methods where there is no shocks, because, for instance, if you are doing electromagnetism, there is no shock. If you are doing plasma in the low density region, which is force-free, there is no shocks. If you are doing general relativity, it's non-linear, but there is no shocks. So there are many cases where you don't have shocks. And then, for those systems that do have shocks, like fluids, for instance, then you need to use some other methods that we are going to develop too. Okay? Well, let's go back to the symmetry hyperbolic, and let's take the example that we already saw a bit. The example of the wave equation. So we have a metric here. You can think of just diagonal matrix with minus, plus, 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 if we are in 3 dimensions. And if we are in n+1 dimensions, you have n of this and this one, only one minus. So the fields here are the values of phi and all the space derivatives. So we have n+1 fields here, or n-1 here. So the equations are just the definition of BA, gradient phi equals to BA, so these are n equations here. Then you have this single equation, which is this, the divergence of B. And then we have all these compatibility conditions with these equations, which are just the curls of B are 0, and they are n plus times n-1 divided by 2. So for instance, in 3 dimensions we have 4 equations here, 1 equation here, and here we have 6. Right? So you have a total of 11 equations, and you have a total of 5 unknowns. Okay? So all these things is in an article by Geroch, which is in the archives, which is like, and I don't remember the title, but it's in the archive of some years ago, some set of lectures he gave. I recommend this article because it's very good, it's very nice. It defines many things which are important. And it's a partial differential in evolution, in hyperbolic equation, basically, symmetric hyperbolic. And so this is our system, right? This is the system in first order, and we want to find a reduction of this system. And here Geroch does it very nicely, all as much covariant as you can guess, and it's very nice how this is done. So I recommend, after seeing this, that you look at what is done here. I think this Geroch article is somewhere in the bibliography that I gave. So we will do more terrestrial here. What we do is just take some vector which is time-like, TA, so GAV, TA, TV is positive. No, it's negative. With this convention of the metric is negative. And GA is like this, right? This is okay. And so you take this equation. Out of these 4 equations, you take one, which is this one. So the time derivative of phi is equal to the time derivative, the 0 component, the t component of B, 0 component. And then from this you take the whole equation. So use that, you can write the metric as a TT plus H. H is just this part of the metric, the part with the plus, the Euclidean metric, if you think. So you put this in the equation and you write it like that. And then from out of this you put 1t here. If you put 1t here, you cannot, because the antisymmetry, you cannot have anything in the direction of t here, so this will be space indices. So you put a t here and an h here, and what you get is this equation for this, time derivative of this, and space derivative of this thing. So if you write in components, in space and time components, you got the time derivative of B naught plus the divergence of pi is rho, and the time derivative of pi minus the space derivative of p naught is equal to 0. And this is a system. And the claim is this is symmetric hyperbolic. I think I have a wrong sign here. Yes. This I have a minus. So I have a minus here. Like this. So, and this system is symmetric. Huh? Well, we know because we can substitute this for a vector, any vector, so then 0 components, and this by the space component of a vector, and so this we have a metric here, 1 for this part, for the n0 part, and then we have a metric that has for the ni I'm trying to see what's the best way of writing this. Yeah, we collapse the matrices in one single one. This here is contracted with this, so this is an ni here 0 with a minus because we put this minus on the other side, and here is a vector. This ni is a vector that goes like that. And here we have 0, and this is multiplied by b0 here, and the bi here. And this is a 3 by 3 matrix, so let's put it here. So here when we multiply, we get bi with ni, and this is a minus 2. When we multiply here this one by this, we get b0 times ni, which is this. And here we get the time derivative of everything, diagonal. So you see this metric is symmetric because this is diagonal and this has a minus ni here and ni. So this metric here is 0 minus nx minus ny and minus nz. And in this direction is minus nx minus ny minus nz. 0 here, so it's symmetric. So this is symmetric hyperbolic. So you can do Maxwell's equations. If you go to the article by Geroch, he does Maxwell in a nice way, with in this setting with the F field. Much more covariant. You don't have to choose these things, so it's very nice. So if you want to have a nice exercise and enjoy something, look at this. It's in the article. So here we do in a pedestrian way. We just take these two as the system, the reduction. We forget about these two. Why we can forget? Well, it's not clear that we should forget. But you can show that if you satisfy these equations, and these equations are satisfied initially, and you have the derivative, time derivative of rho minus the divergence of J0, then these equations are preserved in time. That's why, because For instance, if you take the divergence of this equation, you will get the divergence of this equals to 0, so if this is initially 0, continues 0. So you know that in this case at least, and there is a theory about what a constraint means, and the constraint propagation you can prove in general. So we will do that, some part of that later. So we can restrict to this system. So the variables here are 6, the electric field and the magnetic field. And here you can see what is that this thing is symmetric. So again we take this, we contract with some vector to have the time component and the space components. And you contract with to check that this symmetric, you just contract with in one side with a U1 and in a variable U1 and in the other a variable U2, and check that what you get is symmetric when you interchange U1 and U2. And what you get is, from this part, this is the identity, so you get just the scalar product of E1 and E2 and B1 and B2. And then from these curls, you get this in here, so that you are contracting this with the curl here, and the curl, we leave the index free, this is the derivative index, the J. So we contract with the Y index here and the K index here, the other solutions. And from here you get the minus V1 here and the E2K here. And so now you play with the signs of this term. So you interchange this, you get a minus sign. You interchange these two, you get a plus sign. And then you interchange again these two, you get a minus sign. So this sign with this give me plus, and you get here, I'll write it the other way around, E2 of K epsilon K J I B1 of I. And this is the same as that, because we can then substitute this index by I and this index by K, and rename the indices. And so we see that we have a plus sign here, so this is symmetric. So Maxwell's equation is symmetric. Notice that this is the reason that we have a minus here and a plus here. Right? For instance, if you write Maxwell equations with the same sign here and the same sign here, they will not be symmetric. It will be an elliptic equation, and you will try to solve it, and you will have things growing like crazy or things like that. Although naively you can think, okay, I can solve. I just make I can get a numerical code to solve this system and just change the sign, and the code seems to be okay. You can try it, and you will discover that it blows immediately away. It's totally unstable. So this sign is important. Others. Well, there are many systems. Force-free, for instance. Force-free is like Maxwell. Remember, Maxwell is this equation equals to 0, and this equation and here what you do is to multiply this equation by another f, c, b, grad f a, b equals to 0. You say, okay, my f is going to be perpendicular to J. So this equation plus this equation is for free. And this is symmetry hyperbolic. Ideal MHD is symmetry hyperbolic also. Young-Mills, which is very similar to Maxwell. Is symmetry hyperbolic. Fluids. Euler's equations are symmetry hyperbolic. O sea, ideal fluids. There are many dissipative theories which are relativistic, dissipative theories which are symmetry hyperbolic. So there is a big zoo you can solve. Many of the equations, important equations in physics, are symmetry hyperbolic. That's because symmetry hyperbolicity is causal. We have finite propagation speed, and we need finite propagation speed in fluids. So this is one way of getting them to be causal, to be finite velocities. Okay. Now we are going to discuss causality. The causality that comes from having finite propagation speed. So let me define this thing here. These are all covectors such that when you, now we are in a symmetric hyperbolic system, so you have a symmetric hyperbolic system, and so you have an M, and you know that there is a vector N such that this thing is symmetric and positive. And now you say, well, I want to find all the N's such that this is true. Okay? So geometrically you have a surface. This is a surface, say at this point is a surface whose tangent vectors xa with NA are equal to 0, so this surface. So the x are here. And I say, okay, this is a symmetric matrix, positive definite. Now if you take a positive symmetric like this, or bilinear form, and you perturb it, it's still positive definite. If you perturb with something positive, because the space of positive bilinear forms is open. So if you have this thing, some bilinear form, and you perturb, you add something, delta bilinear AB, small enough, this is also positive, right? You can think of, okay, why is this? Because I can take a basis where this is diagonal, and so this is going to have some elements here, and they are all positive. So if I move something with something here, that what we'll do is to change this for a bit, right? Very small quantity, and since these are positive, If you change by a smaller amount, they continue to be positive. So that's the reason why we have this open. So that says that if I have a surface, so an n, nearby n, so some na plus epsilon ka, if I do this, will be still positive if epsilon is very small. So we know that this is not big. This will be an open set. This C is open and contains many planes. Right? Suppose we are for Maxwell, let's say. For Maxwell, you know that the characteristics, so the vectors, the surfaces which are bad, are surfaces that here I can draw it at 45 degrees. So it's something like this. This is a surface where this becomes 0. Right? So this is going to cease to be positive when this ceases to be positive in some direction. So this fails. The first point where it fails is some point where there is a u such that thing for this value, that thing has a kernel. Okay? So we can start moving this up, and this will have a kernel when this thing has a kernel, and this in general will be one of the characteristics. So you can move these planes up and down until you get to the characteristics. Likewise, you can have a plane. Consider this point. You can rotate this plane in this way. Right? We were rotating it up and down. I can rotate it this way. Right? So I can move this plane. Let's use another color. I can use it to come like this. So this line goes to that, and then this thing comes here, and so it's a plane like this, with this line coincides, this rotation along this line. So all these planes will be okay until you hit the 45 degrees, right? And you have a characteristics. So this space is a space of all planes which go up like this and touch this cone here of directions, right? And this is a cone. What is a cone? A cone is something. So C is a cone. Let's use another. C is a cone. Means that if B, A, and B twiddle A belongs to C, then alpha BA plus beta B twiddle A belong to C for alpha beta positive. So for vectors, normal vector is easy to see what it means. Is if you have this vector and you have this vector, then all vectors which are linear combination of them, right? And these are vectors that are here. So a cone is saying 2 dimensions is this triangle up to infinity, this sector. In 3 dimensions, a cone it will be like this, for instance, all vectors here. What is a cone? Let's think about. Let me see what I did here. Okay. What is a cone of the system we saw today? This one that has three vectors here. L1, L2, and L3. You have these three vectors. What is a cone here? So this plane is in the cone. This plane, say that the one that goes almost touching this. It's hard to draw this thing, what I want to draw. Like this. Still is in the cone. This plane, a bit before touching this, is in the cone. So are all the planes which do not enter this region, the blue region here, the green region, right? So the boundary of this cone is the plane that contains these two vectors. So it's a plane like that. A plane that contains these two vectors, right? And a plane that contains these two vectors. Now we are going to do the cocoons, and that will be easy. But you can move all these planes until you touch the vectors, right? And the most you can go is in some directions, you just go to one of the vectors, in the other two, but then you can go and just touch simultaneously two of the vectors, almost touch simultaneously. So these are the cones. So these are the possible, so the cones C are possible Cauchy surface. At a point. So you take a point and look at the cones, and that tells you at that point which are the possible tangents of the surface. The tangents to a surface are called flats. So what are the possible flats? And so you see at some point you can move the surface. So there are many Cauchy surfaces. If there is one, there are many. Just move around this Cauchy surface and they are all okay. So these are the cones. And then you have the cocoons that are the C stars. These are vectors now, the others were covectors. So these are arrows, such that T with Na is positive for all Na belonging to C. And these are cones too, because if alpha T plus beta T prime A times Na, if this is positive and this is positive and these are positive number, this is also positive. So this is a real cone of vectors, of arrows, right? So think up again in in the wave equation, say. There the characteristics lines were lines which were at 45 degrees. So depending on the K, there are lines that comes around like this. The cones, remember, are since all these planes are cones, and so the cocones are vectors which are here, inside here, because these vectors with this surface points in one direction, in the upper direction, right, of the surface. All these points. So I can go up to here, no problem, and this is less or equal, so I can go to the boundary. This is a closed set. I can go to this boundary, but I cannot cross, because suppose I cross it and I come here. For this plane, this is in the future, points is pinching to the future, but for this plane, this one here is pinching to the past. Right? So this cannot be. So the cones for the metric cones are real the metric cones. So it's the whole thing complete. Not only the boundary, which will be the light cone. So light cone is the boundary. Is the boundary of C star. But the cone is all the interior. Okay, these are geometrical concepts which are very important. So you have the cones and the cocones. For instance, for these three vectors that we have before, we have the L1, L2, L3. What is the cocone of this case? Well, it's all the vectors which are inside here. Any vector inside here is a member. So notice that this cone is not smooth, right? It has sides. So you come here and you turn abruptly into the other direction. So there are no smooth cones. The boundary of this thing, the light cone of this thing is not something smooth. Right? Because with the Cauchy surface you can come as close as you want to these surfaces, so it has to be the vectors that are inside here. Clear? It takes a while to get used to it because it's a new concept. So I don't know whether I say this here. Yeah, I didn't say that this was a cone. And this is a cone because the same reason. If I have an Na inside C and then Twiddly inside C, then if I do a positive linear combination, and apply to M, AVA, this is positive and this is positive, so this is positive, right? So it's a cone. So in this case it is a cone of covectors, so Cauchy surfaces, and in the other case it's a cone of vectors. And what is the importance of this? Suppose now I want to say, okay, I have a point here, and I want to see whether I can reach this point, this other, well, what points I can send signals from here with my system of equations. So the signals are going to propagate at speeds less than the speed of the system, which comes from the characteristics. So I have to move in my system with some, I have to move inside, I mean, the fastest I can go is in the characteristics, say this one. So I have a region here where I can move. I can move by characteristics here, and I can use, say, mirrors here. So I put a mirror here, and I send my wave inside, right? Since, for instance, a mirror here, send my wave like this. So all this region, I can send information from this point. So this is the domain of influence of this point. Huh? So I will say that there are all points. So this is locally, right? Notice that I have, this is just a cone, the cocone, C star. Okay? Are all these vectors. If I want to do it globally, so go further away, I will say, okay, the influence is given, is a set now in the space-time, which is obtained by taking any curve here whose tangent vector belongs to the cone. So this will go, we can call causal curves. So they are curves whose tangent vectors belongs to the cone. So the set of all points that I can reach with causal curves emanating from this point is the domain of influence of this point P. That's all you can influence with your equation from one point. And the domain of dependence is the other way around. You say, okay, the domain of dependence of this point are all points that I can reach with a causal curve. Right, so these are curves that at most can go to the speed of propagation of the signals. But they can go slow, right? If, for instance, I send some signal that goes inside here, and here goes around for a while, and then goes out. And so this is okay, because this will reach later because it has been going around here for a while, but it's also a signal sending information. So I can send information from here to here, no problem. So these are the concept of causality. What influence what? And when you have hyperbolic system, you get this causality for symmetric hyperbolic systems. Let's make a break. I forgot. I am talking already for 1.5 hours. Okay, let's convene at 10:45. Okay, we continue now. So let me recount what we see. We have a symmetric hyperbolic system. So we have a set of matrices, bilinear forms actually, such that this is symmetric, and when contracted with some NA, this is positive. So the set C, the cone, is basically the set of all NA, so these are covectors, such that this is positive. And this stops being positive when it hits a point where this thing has a kernel. So there is a vector here when you contract this is 0. So that's a point of, it's a characteristics. It's a characteristics of the reduced system. The characteristic of the reduced system have the characteristic of the physical system plus other characteristics that appear because you multiply by the matrix R. Remember that this thing here in general for a system with constraints is some matrix multiplying the matrix of the whole system. So this thing here, say, suppose that for some k, this has kernel. The kernel can come from this, or can come from this. But for sure, there will be the characteristics of this kernel are going to be here, and there will be some other characteristics that one chooses by choosing a reduction. In general, there are more characteristics. For instance, and one can try to have all the extra characteristics inside the Lie count of the real characteristics. For instance, in Maxwell's equation, if you do the reduction, you have a characteristic that is just this line here. All the planes that go through this line. So all planes like this. But this is inside this one, so the cone is this one here. So it's okay. But there are more characteristics. So once we have the characteristics, we have this cone and the co-cone, right? This comes automatic. So these are all the vectors PA such that PA with NA is bigger or equal to 0, and this is closed. It's a closed set is really a cone in the sense that it's closed and contains the tip of the cone. So it's all here inside this. And the boundary of this cone is what in general relativity, when you are talking about the cone of the metric, is the light cone. But in general it's some other light cone. It's a cone where you have the propagation of free waves. And we saw that these cones might not be smooth, might not be like this. Right? You have for this system of 3 vector fields, you have a cone like this. For Euler's equations, for instance, if you do this, you get some cone, which is given by the propagation velocity, the sound velocity. So there is a cone. Actually, if the velocity is 0 of the fluid, is the sound velocity. If the fluid is moving, this cone is transformed, right? Because the motion. So it will be, instead of being like this, it will be, suppose the fluid is moving to the right, will be a cone like this. So the standing cone like this is when you are moving with the fluid. Otherwise it's a cone that is moved to one side. Any question about this? No questions? Okay. So now we go to understand all this domain of dependence, propagation, with the real theorems, with real results. And those come from the energy estimates. So our system of equation now is something like this. Equals to some source. And we are doing this calculation first for linear systems. So F, M and F depends on points in the space-time. Okay, but not on you. So what we are going to see is the following. Multiply this by u. Let's say we'll define this quantity. Okay? And we take the divergence of this quantity. And this is when we put the gradient here, we get the equation. So you get UA times FA. Then there is, when the gradient acts here, you get UA divergence of MAB, UB, and then you get gradient A, UA, MAB, A, UB. But this here is again the equation because this is symmetric, right? So this is the same as BA. So this here is an F also. So the end result is 2 UAF A plus UA UB gradient of MAAB. Okay? So since this is a divergence, we can take, let's use it here. You can take some region. Let me draw this region here. Let me draw it like in 2 dimensions only, so that we take a region. We have a sigma naught here, and then we take a region like this. This is sigma t, and this region here is omega. The normal here is NA, and the normal here is N twiddle A. Okay? The normal going up. So if we take the integral over omega of this divergence, we can use Gauss theorem, and this will be the integral of sigma naught of UA MAAB UB and NA, but with a minus sign, because we have to take the outgoing normal. So the normal outgoing will be this one. And then we have the integral over sigma t of the same thing, right? And this has this, right? And so this, on the other hand, is equal to the source. We have all this, right? So this is equal to U A F A plus, so this is the integral on omega of U A U B, this divergence. dV. So we have this inequality. So it says that if I do this integral here, this integral here, that is this one, if I put it on the other side, this is equal to the integral here, this one, plus the volume integral, actually with a minus. Right. And this is called an energy estimate, the basic energy estimate. Syperbolic system. Right. Let's see what it says. We can do something very easy, for instance, and say, okay, assume that all the coefficients of my equations are constant. So that, or that, better that this divergence is 0. Right? This, if I take Maxwell in Cartesian coordinates, etc., this is true. But in any coordinate, actually. If I take the wave equation, it's true, etc. So that will give me many results right away. And suppose I have two solutions. I give initial data. Yeah, suppose I have two solutions with the same initial data. I want to show that they are the same. So I assume I have initial data, UA in sigma naught is equals to some U0A, one solution, and I have another, suppose sigma naught is the same. And I want to show that the solution is unique. Let me do first with f equal to 0, with the source equal to 0. Then we do that. So all the thing is 0. And then what we have is that delta u, so the difference between these two solutions is u1 minus u2, and this satisfies the equation with 0, the same equation, right? Because these equations are linear. But the data, the initial data of this, so delta UA at sigma 0 is 0. So what we have is, we conclude from this inequality here, this is 0, and we have these two terms. This is 0 because here I want to put delta u, and delta u is 0. So we have that this thing is 0. So we conclude that this integral here is 0. Because for delta u, this is 0 initial data. So we have this term, and on the other side we have these two terms which are 0 by assumption. So we have already this result. And so if this n is such that this thing is positive definite, that implies, if this is positive definite, that implies that delta u is 0. And the solution is unique. So uniqueness of solutions. Okay? So what is a region where I have a unique solution? Imagine I can start now blowing this region. So I start with some NA such that is inside the cone at every point. And so I start blowing up like this. So this NA, twiddle A are all, then with this twiddle A is still positive, or all inside the cone. But there will be a moment if I start blowing this up, where this thing is going to, for instance, it's going to be touching a characteristics. Say there is a characteristics here. This is the propagation cone, right? At this point. So the signals are propagated here. So if I start moving, there will be a point where I touch this. And when I touch this, say, I start moving this, blowing up, and I get to a point where I touch it like this. Then when I touch, there will be a wave coming from here and going through here. So if the solution will not be unique passing this point. Even also, if the data is 0 here, for instance, the solution is going to be 0 here, but it's going to stop being 0 here, because there is something coming from outside. So it tells me that I have uniqueness up to here. So the domain of dependence of this is this region here. I cannot go further on. So all these points, the solution at all these points depends on this the data here, but as soon as I move and cross this in here, it depends also on the things that are coming this way. So this is the proof of the validity of the ideas of domain of dependence and influence. So that's the simplest thing. Now we can make it more more interesting. So I don't know where to do it now. Yeah, I have 2 hours. What do we do if we still can prove uniqueness. So we can prove that if the solution is 0 in some part of the initial surfaces, continues to be 0 for a while. And for that, what we do, even if f and m depends on u also, but let's try this case. So m and f depends on the point. So let's continue with this resonance here. So now we have this energy estimate, and these terms are not 0. So what we are going to do is to find an energy estimate which is a derivative of this. So we take the derivative. We are thinking that we are moving here with t, and we take so this we are changing from one of these to the next one, and so we are taking a derivative along this. So let me formalize this. So we have now, instead of having just a sigma t, we have a set of surfaces, sigma tau, right? That they are growing. It's a map from sigma naught. So we have something that is growing like this. It's a one parameter family of surfaces like this. And so what we are going to do is we define the energy at tau equals to this integral on sigma tau of UA M N AB UB and tau A dB. Okay. And now we take the derivative. So we compare up to different points. Right? And so if we compare up two different points, we are doing this thing. We are comparing this surface with a nearby one, right? So that will be that this difference, right? This is the difference divided delta t is equal to this in here, okay? The difference between now this omega is an integral which is just here, since we are comparing these two. And we are dividing this integral by the delta t, so in the limit we get the values here. So we get that this in here is an integral over sigma tau of UA FA plus UA UB, and here we have the divergence. Okay? And this thing we can estimate now. So this is an integral of u times f. So I can write this down as the square root of the integral sigma t tau of ua with some norm, local norm, square, let me use only one bar to indicate that we are making norms in some finite dimensional space, and so that I reserve the 2 bars for the L2 norms and so on. So we say this square times this square for the first term. For the second term, we are going to use the maximum norm of this. So we use the maximum of the norm on sigma tau of this thing. And here we have the norm of sigma tau of UA square. Right? And now we have this product here, and so we say okay, and there was a 2 here. These 2, I was forgetting these 2. Because that makes the calculation easy. So this here we have 2, some number times some other number. So I can estimate this by this square. So I have sigma tau UA square plus this other term. The square of this. And then we have this other. So I can collect this one with this and say this is less or equal to 1 from here plus the maximum of this times the integral of sigma tau of epsilon of u a square plus the source. So now this we can estimate, we can bound this. Since the M was positive, we can bound this by the energies. This is less or equal to some constant times the energy. Okay? So we get an equation of this type. And here I put the norm of F in L2. So assume that this thing is finite in the region, so that M is, say, differential. So this is finite in this compact region we are working. So this is less or equal to some constant, and there was another constant here. Some constant twiddle, epsilon, the energy plus F. Okay? So that says that the energy will be bounded by Y. What is Y? Y is the solution of the equation with equality. So the energy is bounded, and furthermore, if this is 0, when F is 0, then E is bounded by the initial energy. So when you integrate, this is bounded with this, with Y equal to epsilon at 0, tau equal to 0. So if F is 0, then this is bounded by the initial energy. E to, let's put it okay, complete. So if this is not here, the solution to this is the exponential, so this is the e to the c twiddle tau times the energy at t equal to tau equal to 0. So now we can do the complete case. Suppose you have a solution U1, so U1 satisfies MAAB grad A equals to FA, and we have the other solution, so we have AB grad A U2 satisfy the same, so the difference satisfy an homogeneous equation. Delta U is 0, and if delta U initially is 0, then the initial energy is 0, and so this energy is also 0. Implies delta U is equal to 0 for all omega in the domain of dependence. Of sigma 0. Okay? So if we have here the initial surface, I take this This is sigma 0. And I take two solutions of the same equation with the same initial data, then the solutions coincide in some region like this. Okay? But I cannot write it. Okay. So in a region like this. Doesn't have to be like that. Okay. What is the domain of dependence of this? So it's a region I can get just blowing this region like that with surfaces where n is in the cone. Okay? So the n has to be in the cone all the time. And then I have this estimate. You might ask, well, what happens? I have some energy, physical energy. For instance, I can take a scalar field or a Maxwell's field and build the energy momentum tensor. And I have an energy, right? If I have a Killing vector field, for instance, or some other fields, I have this. And I can use this as my energy. And the answer, if you do that, you will find the same energy. So this thing we are computing here is basically this energy. So you will contract this with your energy will be TV and A. That's the thing you integrate over every surface. And here you use that is the divergence of T is 0 because of the equations. So this term here, when you get this integral here is just TAB grad A TV. If this and this is 0, for instance, if TA is a Killing vector field because this is symmetric, so this is the same as this, and if T is a Killing vector field, this is 0. If not, it's no problem. You get some energy growth as we saw here, but this what it does is change this constant situated by this factor, but nothing else. Okay? So this is a relation with the physics. Actually, it's the same thing in a more general way. For all symmetric hyperbolic systems you want to treat. Okay. I'm thinking what I'm going to do next. Probably I will change subject now. Then we will continue this. There are many more things to do here, but I think it's too much for today. So I will stop here this part. We will continue and we'll discuss in a linear case. But at the moment I'm going to switch and do something that is important for the lab. So I will open a new notebook. have some version of it. See. Let me check something here before.